Okay, I think this is going to be one of those "Is Math Real" podcasts because
it's going to be one of the what?
Well, about a year ago, we had just Sam and Nick and me, and I was having technical issues. So I let Sam and Nick talk about is the "Is Math Real" question, and they went off into deep waters. And I was crawling under my table trying to find the cable. I still don't know if that was a good episode or not, but
well, Sam defended Hilbert, which greatly surprised me. And he thought that most people don't take Hilbert's foundational position seriously, since Gödel proved the incompleteness theorems. But he heroically defended the Hilbertian position in foundationalism, and I expressed skepticism.
Which is what? Can you clarify for me?
Well, I was skeptical of the Hilbertian point of view, and that it's going to prove very, it's a complicated issue because Hilbert's philosophy has been reappraised over the past few decades. In fact, I've been reading a book on and off over the past couple of months about what the heck is the name of it. I sent a link of it to Sam so he could see it too. But if you look at the project of the axiomatization of mathematics, certainly that's a very vibrant area of research. And if you think of Hilbert's contributions to the technical aspects of foundationalism, that's still a very active area of research. But the more strictly formalist stuff is out of favor right now, and the distinction that Hilbert made between real and ideal mathematics has not caught on well. I mean, a person could return to it and discuss it again, but it's not in favor among contemporary philosophers of mathematics.
Let's see, that was that was episode 77. If you want to listen to it, Buck.
Okay.
And
77.
Of course, just go to the spreadsheet and scroll down to episode 77 and click on it.
I would be interested to get a thumbnail sketch of Hilbert's view. Is math real? I mean, it sounds like you're saying there isn't a definite, clear yes or no.
Well, the takeaway message for Hilbert these days is that Hilbert would be characterized as a finitist. So he would hold that that finite mathematics is real, and the real deal, as it were, genuine mathematics, and all the Cantorian elaboration upon that is. He didn't deny Cantor. In fact, there's a famous passage where he talks about how we won't be kicked out of Cantor's paradise, but he consigned it to what he called ideal mathematics. So he sort of shunted it off to one side and wasn't interested in it in the way that, say, logicists like Frege and Russell and Whitehead were interested in it. Nor was he as interested in condemning it as the intuitionists like Brouwer and Heyting, were interested in condemning it. But these are all early 20th century perspectives in the philosophy of mathematics, and the contemporary milieu has gone on to neo-empiricism in Kitcher and Tomasko, and constructivism of many different stripes in Michael Dummett and the people who have studied under him, et cetera, et cetera. So the problem set in the philosophy of mathematics has changed significantly over the past 100 years, even though almost any textbook you pick up will talk about the classic phase and the foundations of mathematics in the early 20th century when there was so many mathematical logic was coming to be used, and Gödel proved his incompleteness theorems, and all this other shit was going on at the same time.
So I don't know the difference between, like, when you contrast Hilbert and Cantor. Was that the contrast you were drawing?
Yeah, because it's set theory that becomes the real point of
contention.
Contention, because in the late 19th century, Cantor pretty much single-handedly invented set theory, and this both created the theory of transfinite numbers, and it.
Okay, wait. What are transfinite numbers?
Transfinite numbers is a systematic way to think about numbers in an infinitistic context. That is to say, finite mathematics just deals with the kind of things you learned in grade school, which philosophers of mathematics call primitive recursive arithmetic, PRA. So it's just basically you're following a bunch of finite set of rules, and like when your teacher shows you how to do long division or long multiplication, there's no creativity involved in it. You're not doing proofs like in Euclidean geometry. You're just following a bunch of rules. And so it can all be laid out in a finite scope. But mathematics was always bedeviled by a lot of paradoxes involving the infinite, and most people just put it to one side and said, we're not even going to deal with this. This is crazy. But Cantor actually came up with a way to mathematically talk about infinite numbers in a systematic way. And to do this, it just as important as the theory of transfinite numbers, perhaps more importantly, bless you, is he created a discipline that's known as set theory, which is perhaps the most abstract branch of mathematics that's been created. And it involves all kinds of theoretical difficulties. As soon as it was people after Cantor, the next generation of mathematics tried to produce.
Well, wait a minute. I don't get that at all, because to me, set theory is not advanced. It's like the most basic.
Well, you have
apples. These are oranges. These are bananas.
But when you pursue it, it gets very difficult very quickly. And because it becomes the basis for the theory of transfinite numbers, you could, one of the biggest things that separated the early foundationalist philosophers of mathematics was.
Okay, hold it. Foundationalist. What's that?
The people who attempted who weren't content just to say 1 + 1 = 2. They wanted to say, why does 1 + 1 = 2? Or do we just have to stop there? Or can we offer a foundation for mathematical knowledge? Is mathematical knowledge autonomous? Or does it depend on something that's more fundamental? So
foundationalists fall on one side of that question versus the other?
Well, the early 20th century philosophy of mathematics was profoundly foundationalist. Almost everybody offering an answer had a different answer. The logicists said logic is the foundation of mathematics. That's Russell and Whitehead and Frege.
Okay.
The intuitionists like Brouwer and Heiting, they said it's just an act of intuition, and you can't go below that act of intuition, but they elaborated on that to a significant degree, and they're also famous for denying the law of the excluded middle and doing without it. And the formalists like Hilbert, well, there's a lot of different formalists, but Hilbert was, we're going to finitely axiomatize mathematics, and when we do that, that's good enough. But that project got put the kibosh on by Gödel, who proved that even arithmetical sentences, when properly formalized, there is no completeness proof. I mean, you can prove the incompleteness of even, the most basic mathematics. But Gödel's proof is completely relative to the formal system created in Principia Mathematica. You can translate into other formal systems, but that was, at the time, that was the formal system that was used. And all of the well-known paradoxes can be reformulated in almost any formalism that you care to name. But that's the whole challenge of the next generation of mathematicians after Cantor, wanted to formalize and axiomatize the intuition's underlying set theory. And this is what became very contentious because some of these axioms are very simple. The union axiom and the separation axiom and the foundation axiom. Well, I don't care much for the foundation axiom, but I won't get into that now for the moment. But the guy who did the real spade work was a Zermelo, Ernst Zermelo. Zermelo came up with an axiomatization of set theory that is still essentially the one used today after many revisions. But he realized that mathematicians were making an assumption, and so he explicitly formulated this assumption as one of the axioms of his systems. And one of that assumption was the axiom of choice. And the axiom of choice says that when you have an infinite set, you can break it up into an infinite number of subsets, and you can choose one element from each of these subsets to make another set. And as weird as that sounds, it's actually demonstrably equivalent to several other assumptions that are used in set theory. For example, the principle of trichotomy, that for any two real numbers, either one is greater than the other or they're equal. But the real bugbear of the axiom of choice is that it's a radically non-constructive axiom, and that bugged the shit out of most mathematicians.
Wait, run that by me again.
It's a radically non-constructive axiom.
What is
the axiom of choice? Because it says a set exists, but it doesn't tell you how to construct that set, and that is what became the crux of the next 50 years of research in the axiomatization of set theory.
Okay. I always thought the problem with sets was that, of course, I'm looking at it more from a pragmatic view and its relation to our observed reality. And as far as I can tell, reality doesn't really divide up. Reality doesn't seem to care whether something's an apple or an orange. And things that are apples, you look at any individual apple, and it's not exactly one apple. It's because no two apples are identical. So there's no such thing as like one apple if we're going to be precise. And, how much of a stem can you have? Well, these are all things that we're deciding, and there's no indication, as far as I can tell, that nature cares about that. I don't think that nature actually does this.
No, we model nature with these things. Nature doesn't model mathematics.
And it has been said that all models are false, but some models are useful.
Yes.
And I think I can
pragmatic vindication.
If you give me a pile of apples and oranges, I can very reliably sort them into two sets without error in nearly every case, which is good enough.
Good enough for finite mathematics, that's for sure.
Good enough for modeling reality. But
the problem there comes in of what Hilary Putnam called indispensability arguments, because you can prove that in order to do these simple tasks of finite mathematics, you're implicitly invoking concepts of infinitistic mathematics, and therefore you need this whole conceptual framework, or you can't even do the most basic things in primitive recursive arithmetic.
I'm not sure I believe that. I mean, I think you can say, well, we can demand that this activity require a justification, but again, I don't think that that's unless you take that as an assumption. I'm going to go with Gödel on that one. That if you just don't care to do it, there's no real requirement that you do so. For years I thought Hilary Putnam was a woman.
He's not. He died Just
Not
a
that
few
it's any of your
years ago,
business.
I wrote a blog post when he passed a few years ago.
Oh, okay. What was that, Paul?
Just no, never mind.
It's not your business what the gender of Hillary Putnam is.
Yeah. Well, I mean, we tend to care a lot about that sort of thing, but I don't know that we should.
Well, like whether should we care about the difference between apples and oranges? Well, yes, if we have.
It depends on what you're hungry for, right?
It depends on what you're hungry for, what your preferences are,
or what you have a deathly allergy to.
Or
I wouldn't want to put oranges in a Waldorf salad, but then again, I don't want a Waldorf salad. So, but the idea, the basic set theory that we all learned as undergraduates works very well for nearly everything, but people do argue incessantly over certain, usually the infinities, which are of very little interest in the real world.
Yeah, that's exactly how I feel. I'm like, this is something they thought up and just said, well, it's something so big that it's just infinite. It goes on forever. It has no limit.
But no, that's exactly what Cantor put the kibosh on, is he showed how you can talk systematically about infinite, is not just saying, oh, it's so big it never comes to an end. I mean, Cantor was able to, if you buy into the axioms of set theory, including what are called large cardinal axioms, then you can say that there are infinite sets that are larger than each other and that they form a hierarchy of infinite sets.
Yeah, and Cantor's proof of that is famous and very easy to understand, going from the integers to the
diagonalization.
reals. Yeah.
Diagonalization of the reals.
Yeah, and when I first saw that, I go, oh, this is just like, this can't be that easy. but yeah, and the thing is, in computing, we have we can represent an extremely large number of numbers, but we can't represent an infinite number of numbers. Everything's a finite state, and so I'm still on the.
If I write an infinity symbol, how is that not representative of an infinite?
No, I mean what you could actually represent with a realizable a finite sentence in bits cannot represent an infinite number. Obviously, you can
computers can only work with a finite number of bits over a finite period of time. Right. The philosopher William Barrett said that a computer is an embodied decision procedure, and he was right in saying so.
Yeah. So I can't represent an infinite with an infinity symbol, for example.
Well, you can for your conscious purpose of writing it down on a piece of paper and recognizing it, but a computer can't do anything with it because it can't operate for an infinite period of time or with an infinite amount of information.
Yeah, and physics
can it deal with a representation of the infinite?
Well, that's a point of contention.
Well, that's just the the veil across the Holy of Holies. It's not the Holy of Holies itself.
think of the incredible images that have been made of fractals. Now, a fractal ideally would be continued to infinity, but obviously computers don't actually calculate. They calculate them to far more decimal places than a human being could do, because they can do it faster and they can do it more efficiently.
Right.
Yeah.
So when you're looking at a picture of a fractal, it's beautiful, but it's not an infinite representation. Only the mind can conceive of the infinite iteration.
I'm persuaded that there are things that are unbounded. In fact, I think that's been known since the Greeks. Like, for example, there is no largest prime. We know that, but
right.
There's.
But you can't get a computer to spit out an infinite list of primes, because if you started it would never stop.
All you know is that if it computes a prime, there's a bigger one somewhere, and
right, and you can get a proof. You can get a computer that could churn out a proof. If you accept the underlying logic and the axioms that you're working with, it can determine whether a proof is valid or not.
Yeah.
What is it about something being a prime that necessitates there being a larger one?
Oh, that was I think was it Euclid? No, it was some Greek proved that.
It might have been Eudoxus. It might have been Euclid. I can't remember the proof.
It's like a high school level proof. It's real easy to understand.
Right. Yeah. It's basic stuff.
Okay. Can you give me a basic overview of what the claim is?
Well, the claim is that
I understand the claim, but how does that work?
There's no largest prime number. You can always construct one that's larger.
But how does, like, if you find a prime, it means that there's a larger one?
Well, yeah, there is no. The proof is that there is no such if you say that x is the largest prime, that leads to logical contradiction.
Okay.
And
so
it's
how
very
does that
straightforwardly.
Okay.
I'll send you a link. It's real. It's
yeah,
Friday night. I've had like a bottle of wine. I can't.
I'm looking at a proof right now, so yeah, we can send you links. It's an ancient proof. So
if you're a high school student, you don't understand that proof, that you're not college material.
Yeah,
I taught grad school, so I ought to be able to understand this simple explanation.
Take a look at the link in the chat.
Okay.
And like there are many proofs of the infinity of primes. Like Paul said, that the classic proof is a proof by contradiction. So if, like intuitionist, you reject the law of the excluded middle, you have to come up with a constructivistic proof. But there are constructivistic proofs of the infinity of primes, but that gets much more complicated than this basic stuff.
Yeah, I wouldn't want to. Yeah, that's got to be harder.
Constructivism makes everything more difficult.
But it eliminates. But showing that it's logically contradictory is easy.
Yeah.
And I just can't remember the exact details, but
it comes down to the fact that real numbers cannot be represented as rational numbers. Because rational numbers you can't divide by 0, but you have to. So you.
It's simpler than that. It's simpler than that. You say, okay, if this number there's no larger prime, then you construct another larger number that would have to be prime or something like that. It
says let P be any common multiple of this list of primes. There's a finite list of primes, and P is a common multiple of them plus 1.
Well, that would work, yeah.
Now P
it's
is
not
either
the small. It's not the smallest prime neck, but it is a prime.
Sorry?
That is a prime, yeah. But there's probably a number between that and the other primes that's even smaller, but which is greater than the largest prime that you've claimed it was the greatest. Yeah, that's a real simple way to do it.
Okay. If it is prime, then P is a prime, and that was not on our list.
Yeah.
If P is not prime, then it is divisible by some prime. Let's see. And so,
but it can't be because
P is a common multiple of these primes, which is their finite list of primes.
Yeah. That would be a really big number, but yeah, you could do that.
They say if it is a prime, if I'm missing something, if it's maybe I don't know what a common multiple is.
That's taking all of them multiplying together.
Okay, but then they say if it is prime, well, if it's a multiple, it can't be a prime, can it?
No, I think what their point is that if you take the number and add 1, then suddenly it doesn't have prime factors, so it makes it a prime number, right? So
you're taking factorable numbers, multiplying them together, and then adding 1, so it's not going to be divisible by any of those ones you've got so far.
Okay, that's not what it's. If I'm reading it correctly, it's saying that you're multiplying a list of primes, not.
Yeah.
Well, it comes to the same thing, because prime numbers are what the number system is made of, because any non-prime number can be made through the multiplication of prime numbers.
Okay.
You're not adding anything by adding non-prime numbers to it.
Yeah, you multiply two primes, you've got a non-prime. But you
right.
But now,
so
if you take all of the primes and multiply them together and add one, you have a prime. But that's a very long list of primes. But it would be really probably a not practical calculation to do. But if you claim that X is the largest prime, then you've made a claim that can easily be defeated by a simple calculation. Simple, but probably very, very long calculation.
Okay, so let's say I claim 7 is the largest prime. What's the simple? What's the trivial explanation of how we know
7 times 5 times 3 times 2 plus 1 is that would be 35 times 3, which is 105, times 2, which is 210, plus 1, 211. Check it. It's prime.
Okay, so if you
there's a whole lot of primes between that and 7.
Yeah.
The next one is 11.
Which you can find by the sieve of Eratosthenes. Just go through and cross off every second, every third, every fourth, every fifth, ad infinitum. That's the sieve of Eratosthenes that will give you the prime numbers.
That's not a real efficient algorithm, but it works for small numbers.
Yeah, it works for small numbers, and it'll get you the primes between 7 and 211 or whatever Paul said.
Oh yeah, I'm totally on board with that. I'm unclear on the multiplication of primes and then adding 1.
Yeah.
Well, because once you add 1, it's no longer prime. I mean, once you add 1, it's no longer divisible by any of the factors that you've multiplied together, because there'll always be a remainder of 1.
Okay, that makes sense.
So it's a prime number. And
right.
And therefore, the one that you claimed was the largest is no longer the largest.
Okay.
And so you will always be able to find a larger prime. There's a simpler argument, which I can't recall the details of.
Now, there are many, many proofs of the infinity of primes. I was just looking here on this page I linked to, and there is a proof as recently as 2005. Philip Sidek's proof of 2005.
Yeah.
Is that the Utah math department?
The one above that shows 5 different proofs. There's 3 links there, so the middle of the 3 links shows 5 different proofs.
Yeah, a lot of these classic theorems have many proofs.
Yes.
Pythagorean theorem is probably the biggest magnet for math geeks. They proved it probably 30 different ways.
An overdetermined proof, as it were.
Yeah. It's one of those things that, that's the sort of thing where, what my point was, though, that yes, we know the prime numbers are unbounded, that there's no largest one, and therefore there's no largest, and therefore there's no largest number. It's unbounded. Okay. It's unbounded, and that's, to me, is a fascinating fact. But when you start talking about infinities, you're getting into a different territory.
Well, if you use the traditional Aristotelian idea of a potential infinity, which is still a variant of which is used by intuitionists and constructivists, you can be perfectly well just saying all infinities are just, you continue on ad infinitum, and there's nothing more to say. What distinguishes the Cantorian approach and the set theoretical approach is being able to say, well, there are infinite sets of numbers, but some of them are different size. The number of the number of prime numbers is equal to the number of whole numbers.
Cardinality, I think they call it these days.
Yeah. The cardinality of those two sets is the same, just like the cardinality of the set of all multiples of 2 and the set of all odd numbers is the same. But then when you get into real numbers, then you get into a set that's quantitatively larger and cannot be put on this one-to-one correspondence with the whole numbers.
Yeah, no, I can't remember his argument in detail, but Gregory Chaitin has argued that the real numbers don't exist.
Yeah. Well,
because they're riddled with uncomputable numbers.
Well, and transcendental numbers and all that good stuff.
It's
fascinating.
There are numbers with an infinite number of digits that are computable, like pi or the square root of 2. They're computable, but there are, as he's shown, there are numbers that are not computable. And in fact, there's
how is an infinite progression computable? By what definition of
there's
computable?
An algorithm for computing it to an arbitrary precision that is much smaller than the number itself.
Well, n plus 1.
Yeah.
Substitute any number you like for n, and then you get n plus 1. That's a function that gives you, if you substitute 1 for n, you get 2. If you substitute 1,000,000, you get, 1,000,001.
Yeah, but I mean,
you could.
Yeah.
And it's iterable, and whether you want to pursue it within a finitistic context or infinitistic context, like you said, the finitistic context is sufficient for almost all engineering, technological, natural science purposes, etc. And it's only a bunch of, weirdo extremists like me who are interested in transfinite aspects.
I think it is kind of interesting. I just don't know that at least I haven't seen any clear argument that it reflects back to. Now I know physicists hate infinities. As soon as the infinity shows up,
hence renormalization.
That and but they're like, that's why we have two independent major theories of physics, right? The Standard Model and general relativity, because all efforts to combine them by the brightest people on the planet have resulted in infinities. And, that just doesn't make sense physically. So that's why we still have two theories. And a lot of people, really smart people, are still trying to unite the two theories, but, that infinities are stinky, repulsive, nasty-looking things to physicists.
To a physicist. One day, the physicist will be born who studies the theory of transfinite numbers, and they'll say, "Oh, that's how it's done."
Well, I wouldn't rule that out. I would not rule that out.
And I will make a prediction that will probably not come true while we are alive, but I believe that the theory of transfinite numbers will one day be the ultimate setting for cosmology.
Maybe so. I'm not going to rule that out.
The ultimate setting?
You have to have a mathematical theory to produce a scientific theory. I mean, so that when we say that Riemannian geometry was a setting for Einstein's theory of relativity, we mean that he used the mathematical tools developed by Riemann in order to formulate the theory of general relativity. And there were other non-Euclidean geometries but Riemann's were the mathematical tools that made the most sense for formulating the theory of relativity. So what I'm saying is, when the ultimate theory of cosmology is formulated, the mathematical setting for that will be the theory of transfinite numbers, but not anytime soon.
I mean, I actually, when I read Chaitin's book, I thought he's onto something. He believes, and this is more an intuitive statement of his belief than anything he can prove, is that mathematics and physics are exploring the same thing, and but he can't quite put his finger on what it is. And I got to believe that he may be right. He may well be right. We just don't know. Nobody, that there's probably somewhere out there a 3-year-old girl who's going to be able to put her finger on it, but she's not there yet. And, but
have either of you heard of this woman who's her name's Furey, Dr. Furey?
Is this the Iranian chick who got the Fields Medal or something?
No, she died recently. Yeah.
No, she's not Iranian. She's Canadian, I think, and she's like head of a math department at Cambridge or something. She's into octonions.
Octonions are pretty well known, yeah.
Well, it used to be all quaternions, and when I did my first 100-year starship pitch, I was just doing quaternions and Maxwell, James Clerk Maxwell, and then also covered a little bit of the Heaviside Tate debates, where the quaternions, which had been so useful to Maxwell, got sort of the history got rewritten in standard vector representation because it was better known, and that this, from an information management standpoint, this is noteworthy because the decision of representation wasn't made based on the strength of the tools. It was based on things like political infighting and insults. It was Heaviside called quaternions like a hermaphrodite monster. And he had some really great twists of phrase there to insult Maxwell was like such an agreeable guy. He was like, do whatever you want. And there was a society of trying to support quaternions, and they held on for a while, but vectors were just too popular, and it was very weird. It looked to me from a historical perspective like a mistake.
Well, in my field we use quaternions all the time, but
do you use octonions at all?
No. Quaternions are useful for representing a rigid body's orientation.
Right.
And
they don't suffer gimbal lock.
No, they can, but they don't have singularity, but you can still get gimbal lock.
You can.
Yeah. But that's physical. That's not a question of representation.
Okay, let's see. Octonion math. Furey. C. Furey. Let's see. She's at Cambridge.
F-U-R-Y?
It's F-U-R-E-Y. Yeah, I think she's on to something. Let's see. She specializes in Clifford algebras. I'll post a link.
Yeah, I found her web page here. Postdoctoral research fellow in theoretical physics at the University of Cambridge. Main interest in algebras, Clifford algebras, Jordan algebras in relation to particle physics. Collected publications.
That's been around for a while. I mean, I'm sure there's some active research, but not new.
Well, apparently, when she was working on her PhD, she was told that pursuing octonions would be career-ending, and that if she had a sense of survival, she would drop it.
I can believe that.
I strongly suspect the students get told things like that on a regular basis.
They do, and about lots of topics.
The weak ones fold and the strong ones push ahead, whether
Right.
they're
Well, yeah,
parallel or
they're always getting advice about, look, here's where you need to put your effort because that's where we're going to get funding. That's where we're going to get.
This is the hot topic that everyone's
That's where you're going to get
about.
recognition. That's where you get cited. And that's. I don't know if that's a feature or a bug in the way we do guys, but probably a bit.
Probably
of both. Yeah.
Yeah. There we go.
This has been the Unseen Podcast, the unscripted, uncut, and open participation podcast from Dream of the Open Channel. For more information, including show notes for this episode, please visit unseenpodcast.com. You can also follow us on Twitter @PodcastUnseen. If you are interested in joining one or more panels on this podcast, then you can. No subject matter expertise or podcasting experience is required, and we're always eager to add new panelists. Just email unseenpodcast@gmail.com and we'll get you started. The Unseen Podcast is produced by Paul Carr and is released under the Creative Commons Attribution Share-alike license. Music is by DJ Spooky.